This video will focus on ionization energy, both understanding why it increases each time we remove an electron, and also helping to identify when each atom has a large jump in ionization energy. Ionization energy, again, is the energy required to remove an electron from an atom to make it into a positive ion. That electron is being completely removed and being added to another atom's orbitals. All the graphing activities we've been doing has been looking at the first ionization energy, which is the energy required to move the very first electron from any atom. That electron will be removed from the valence shell of an atom, which are electrons in the outermost energy level of any given electron configuration. So for sodium, it'll be its S1 electron. For fluorine, it'll be one of the P5, right? One from the P orbital, there's 5 there, it'll take one of those. So whatever furthest out. But you can talk about more than just a first ionization energy. You can also talk about a second, and a third, and a fourth, and a fifth, etc. What those mean is that you've taken away one electron, that's the first ionization energy, and when you take away one electron, you leave behind a positive 1 ion. Now, you can measure the second ionization energy, and that'll be the energy required to move a second electron. So if you look at this table in front of you, the second row is representing the second ionization energy. So lithium and beryllium are already a +1 ion, and now we measure how much energy it takes to take away the second electron, making it a +2 ion. Then once it's a +2 ion, we can take away a third electron to become a +3 ion and measure the energy it takes to remove that single electron. So each ionization energy is measuring how much it takes to take away one electron. It just depends on what it's taking that one electron away from. If it's taking away from a neutral atom, that's the first ionization energy. If it's taking away from a +1 to make a +2, that's the second. If it's taking away from +2 to become a +3, that's a third, etc. Something you'll notice if you look at this table also, and this trend repeats for every atom, is each subsequent or additional ionization energy requires more energy to remove that electron. To understand the reason, you have to understand why you need energy to remove an electron in the first place. So the reason an electron is hanging out in an atom again is because it's attracted to the nucleus. That nuclear charge is positive and the electron is feeling attracted to it. In order to remove that electron, you have to put energy in that overcomes the force of attraction to the nucleus. So the first ionization energy is the energy required to take that first one away and let it join another orbital. And that's the amount of energy required to break, essentially, the attraction with the nucleus. Once you take away one electron, essentially you're not affecting the nuclear charge at all, but you are affecting how many electrons are repelling one another. So remember, always in terms of attraction, we have the push and the pull. We have the pull of the nucleus and the push of repulsion. And by diminishing the repulsion of the electrons, essentially all the electrons can move a little closer, and now they have a stronger pull from the nucleus because simply distance. The distance is pulling, the pull is going over a shorter distance, and now we have a stronger pull. Okay, so the nuclear charge isn't changing, but the effect of the nuclear charge is changing because I'm diminishing the repulsion from the electron. So after one, all the electrons get pulled a little closer and they have a stronger attraction to the nucleus. So to remove the second one, you need more energy. Now after you remove the second one, now you've decreased the repulsion even more. The electrons get pulled in even stronger, and now it will take even more energy to remove the third. So each time you remove electrons, you are not affecting the nuclear charge, but you are affecting essentially the effective nuclear charge of how the electrons are experiencing it, because each time they're being drawn closer because of your diminishing repulsion. Now, something we notice that if we look at a table of ionization energies and kind of look for trends or patterns, which is what we do here, every single atom at some point in time, after you remove one electron or 2 or 3 or 4 or 5, there's always a jump in how much energy it requires to remove the next electron. So for sodium, it takes 498 to remove one, and then to remove the second one, it takes 10 times that much. And for magnesium, of course, it removes one, and it takes more energy to remove the second, but then to remove the third, it's 7 times as much, right? Aluminum, you can remove the first, and the second takes more energy, and the third one takes more energy, but now to remove the fourth one, it takes 5 times as much energy. And that pattern continues. If we look through this entire table, you'll notice each time it's like hard, harder, 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 okay, impossible, essentially. So eventually some of these energies listed here are energies that nature just won't give in order to remove the electrons, so they're essentially impossible. If you take this pattern and reflect it on the table, what you'll notice is each of the super, super hard electrons to remove are always the electron, that first electron in the inner configuration of S2p6. So remember, electrons are willing to gain and lose electrons in order to become like noble gases, S2p6. But what we find is when we're removing electrons, once they become S2p6, it's really hard to remove one more additional electron. And partially it's just a destabilizing thing, and partially it's just the strength of that nucleus in terms of the pull, but that's the pattern. So each time, if you're trying to predict, like, when will the huge jump be? It'll be always the next electron after it's achieved its noble gas configuration. So aluminum likes to become a +3, and that's okay, but it's that fourth electron then when there's a huge jump. Sulfur doesn't super like to remove any electrons. You can see all of the numbers are super high, but sulfur can remove all of the S2p4 that it has. But now if you're going to dip into its noble gas, S2p6, it's going to be really hard to do. So those are the main concepts of ionization energy. Have a nice night.